Welcome back to Math 104. Consider the experiment of rolling a fair die 5 times. What is the probability of obtaining a 6 on the die exactly 3 times? The key to solving this problem is to realize what kind of problem it is, namely a sequence of Bernoulli trials. It does fit the pattern of the other problems we've seen in this set of videos. The experiment itself consists of 5 Bernoulli trials. There are 5 stages of the experiment, and each stage either involves obtaining a 6 or not obtaining a 6. Let's write down some relevant numbers. Capital N is the number of Bernoulli trials, and there are 5 of them. Then little p is the probability of quote-unquote success on each individual Bernoulli trial. If we think of obtaining a 6 as a success and obtaining not a 6 is a failure, then little p equals 1/6, which means that 1 minus p equals 5 over 6. We are asked to find the probability of 3 quote-unquote successes in 5 trials, in 5 rolls of the die. That is exactly what our formula knows how to compute. 5 choose 3 times 1/6 to the third times 5/6 to the second. Any one particular sequence of 3 of these successes and 2 failures, 3 6s and 2 non-6s, any particular sequence has probability 1/6 to the third times 5/6 squared, and then the overall probability of 3 of these quote-unquote successes in 5 trials in any order is 5 choose 3 times that number. When we compute, this turns out to be approximately 0.2315. Not particularly likely to get 3 of these successes in 5 attempts. Each individual success is so unlikely, 3 of them in 5 attempts, even though they're allowed to come in any order, is still pretty unlikely. Let's look again at this experiment of rolling a fair die 5 times, and finding the probability of rolling a 6 exactly 3 times. What if we had regarded obtaining a 6 as a failure instead of a success? What effect would that have on the result, and how would the computation go? Well, in that case, n would still be 5, but now little p would be 5/6, and 1 minus little p would be 1/6. If rolling something other than a 6 is a success now, we have a 5 out of 6 chance of success on each roll. But now, the event obtaining a 6 exactly 3 times, this is now 3 failures in 5 attempts. 3 failures because we're still talking about obtaining a 6. If obtaining a 6 is a success, then our event is 3 successes in 5 trials. If obtaining a 6 is a failure, then our event is 3 failures in 5 trials. But now what happens when we write this down? But now what happens when we apply the formula? The formula knows how to find the probability of so many successes. So if there are 3 failures, that means there are only 2 successes. The probability of a success is therefore being raised to the 2nd power, and the probability of a failure is raised to the 3rd power. But 5 choose 2 is equal to 5 choose 3, because of the symmetry in row 5 of Pascal's triangle, the symmetry in any row of Pascal's triangle, and 5/6 squared is a number, 1/6 cubed is a number. We can multiply them in the other order without changing the value of the expression we're computing. This expression here is exactly what we found back when we were looking at rolling a 6 as a success rather than as a failure. So if we look at it as a failure, we write down this expression. If we look at it as a success, we write down this expression, but these 2 expressions are in fact equal. What's the conclusion? It doesn't actually matter which one you think of as success and which one you think of as failure. For any specific computation, you have to pick one and stick with it. When 10 fair dice are rolled, what is the probability that exactly 5 dice show a 1 or a 2? Assume that the behavior of each die is independent of all the others. Pause a moment and think, what is each Bernoulli trial in this experiment? How many trials are there, and what does each one look like? The Bernoulli trial here is to roll 1 die, and see if it shows a 1 or a 2, or if it shows something other than a 1 or a 2. Thus, success can be thought of as obtaining a 1 or a 2, and failure as obtaining a 3, 4, 5, or a 6. As we've seen, we can look at it the other way around, but within each trial, either there is a 1 or a 2, or there is a 3, 4, 5, or 6. Setting it up this way, where 1 or a 2 is thought of as success, there is a 2 out of 6, which is 1/3 probability of a success on a single Bernoulli trial, and therefore a 2/3 probability of failure on a single Bernoulli trial. Our question is about the likelihood of 5 of these successes in 10 trials. So n equals 10, k equals 5. And we write down, according to the formula, 10 choose 5 times chance of rolling a 1 or a 2 raised to the 5th power, because we're asking about that happening 5 times, times the probability of the other thing taking place, also to the 5th power, because if there are 5 successes, there are also 5 failures in these 10 attempts. This is approximately equal to 0.1366. Here's another dice example, but it's a little bit different. In a certain dice game, each time you play, you roll a pair of fair dice, and if the sum equals 8, you win. If you play the game 5 times, what is the probability of winning exactly twice? The wording here indicates that there are 5 trials. We are asked for the probability of the trial turning out a certain way twice, and turning out the other way 3 times. What is the Bernoulli trial here? It is to roll a pair of dice, because that is the only thing that makes sense in terms of how the problem is stated. The problem is stated in terms of rolling a pair of fair dice and seeing if the sum equals 8. To help us see that that's the thing to focus on, this is described in terms of winning and losing. If the sum equals 8, you win. Otherwise, you lose on that particular roll. Therefore, success means that the sum equals 8, and we have to think, what is the probability of the sum equaling 8? Here we have to go back and think about the experiment. We have to go back and think, what does it look like when you roll 2 fair dice and find the probability that the sum equals a certain number? This is something that we've thought about before. This is an experiment with 36 equally likely outcomes. And if you count them, there are 5 outcomes in which the sum equals 8. For example, you could roll a 2 and a 6, or you could roll a 3 and a 5, you could roll a 4 and a 4, you could roll a 5 and a 3, or you could roll a 6 and a 2. Those are the only outcomes which contribute towards this event that the sum of the 2 dice equals 8. You couldn't roll a 1 and a 7, for example, because then somebody would be cheating. So there are only 5 ways, but there are 5 ways to obtain this result. That means that on a single roll of this pair of dice, the probability of a success, the probability of winning that roll, is 5 out of 36, and therefore the probability of failure, 1 minus 5/36 equals 31/36. Our probability of exactly 2 wins in 5 attempts equals 5 choose 2, 5 trials, 2 successes, times probability of a success, probability of a win, raised to the 2nd, times probability of a loss, raised to the 3rd power. This problem is the same as the others we've looked at in terms of the overall form and the overall thought process. What's different is that in order to find this probability, little p, we had to think a little bit more about the experiment. When we compute, this turns out to be approximately 0.1232, a little better than 12% probability that this event occurs. That's not so unlikely. Before going on to the next video, answer the following questions about the same die rolling game, where you roll a pair of dice 5 times. On each roll, either the sum equals 8 or the sum doesn't equal 8. And if the sum does equal 8, then that roll was a win. What is the probability of winning at least twice? And what is the probability of winning at most once?